Namaste, Sati students. I'm Priyanka Rajeev from Department of Mechanical Engineering, IIT Kanpur. This is lecture 6 of Laws of Motion, and today we will be discussing about tension. So, tension is okay, one second. Step. So, 1 second. So, slight problem with the screen. Southeast students, I'm Priyanka Rajeev from Department of Mechanical Engineering, IIT Kanpur. This is lecture 6 of this chapter, Laws of Motion. And today we will be discussing the topic tension. So, tension is basically a pulling force. Okay, so we will discuss about tension, the type of force called tension when we are dealing with objects like rope, string, cable, which are like mostly cylindrical, long objects, right? So this pulling force, the tension force, is kind of like a so example, if you consider this as a string, then it is a pulling force which is transmitted axially. Axial means along the axis. For example, if you consider the string as a cylinder, then this is transmitted along the axis of the cylinder. So that is called as axial transmission. So this tension is a kind of like a pulling force which is transmitted axially, and we will observe this kind of forces mainly in a string or a chain or a rope or similar objects, which are like basically we treat it as a one-dimensional object. Like for example, you can treat we don't consider the width of the rope, right? Mostly we don't consider the width of the rope. We only consider the length. Okay, so the length is the major or dominant dimension of this object. So we are treating this as a 1D object. Okay, so rope, cable, what is the specialty of those kinds of object? It is kind of like a one-dimensional object, which is like we can assume that this this rope consists of small particles which are arranged continuously, right? So that is like a one-dimensional object, a continuous object. Okay, this is how you can, these both are equal. This is the equivalent form of this rope. So you can treat each and every particle of this rope as single object, and they are like clustered together to form a one-dimensional object. So that is how we treat rope or a cable. Okay. Now, this tension can be described as an action-reaction pair. Okay, so we will see about it later. So you have to imagine this form, this this kind of form when I'm talking about a rope or a chain. Okay, you have to imagine this rope as a collection of particles of individual particles inside the rope. Okay, so then only when I'm explaining the action reaction pair of forces acting inside this rope, you will get to understand that. You can visualize that that kind of forces later. Okay, so you can imagine that kind of forces, how it is acting inside a rope. So tension basically means stretching. Okay, that is a Latin word. So tension means stretching. So when you are pulling a rope, you can see that the rope will be, initially the rope will be lying like this. When you pull it, what will happen? It will be straight, right? So that is how, so it is kind of like a stretching. So this tension is kind of like a stretching stretching. Stretching the force which enables this rope or chain or such structure to stretch out to be in a straight line. So that is tension. Then like any other force, we treat tension also as force. So that means whatever laws we have learned, the first law, second law, third law, everything is applicable here also. Okay. Now what is it? Okay. uh, so now we are talking about from the perspective of solving a problem. Okay. So you know that whenever we are studying something, we idealize that object first, right? Like for example, we were talking about a smooth surface, right? A smooth surface where friction is not acting. When we are talking about a ball falling from a height of edge, we don't talk about air resistance. Likewise, here when we are solving the problem of tension, you can assume a string without mass. For example, very thin strings are there. For example, the string which you use for stitching clothes. Okay, that is having a negligible amount of mass in it, right? The whole what to say, the whole bunch of uh, uh, that chain, or the what we say, uh, yeah, so that kind of rope or string is will be having less than 50 grams. So uh, this is the kind of uh, like string which we are dealing when we are talking about string without mass. Okay, so a negligible amount of mass it will be having, so we can practically ignore the mass of that string when we are solving the problem. Negligible amount of mass. Okay. Now we will be talking about string with mass. For example, have you seen towing of a car? So towing is like, this is a car. Okay. If I talk about car like this, okay, I don't want to um, ignore the aerodynamics. So if I'm talking about a car like this, okay, a car like this, if suddenly on your way back to home, you were driving your car and it got stuck somewhere, it broke down. So what we will be calling a road assistance vehicle. So road assistance vehicle will be something like this. Okay, so they will come for what? For towing your car like this. They will pull. Okay, there will be a hook and it will pull like this. So that is a kind of uh, this kind of rope will be very huge in size. Okay, very huge. So those will be having a considerable amount of mass. So that mass we have to consider when we are solving problem. Okay, so this will be having a considerable amount of mass. Okay, so we should understand when to neglect the mass of the string and when to use it. Basically, the rule of thumb is that if mass of the rope is given, you will use that when you're solving the problem. If not, we will neglect it. Okay, so string without mass. So how it acts? Okay, so string without mass. Consider a string like this. Okay, so this is a string, and this is a force exerted on the string, and you're pulling an object of mass m. Okay, so you're using this force F, you're pulling a object of mass m, and using a string without mass, like, or of a mass with negligible amount of mass. Okay, so just like how I was explaining before, if you're imagining this rope as a collection of particles like this. Okay, the rope is like this. If you imagine the collection of particles like this, and I'm only showing some of the particles here. So this is one which is near to the object. This is also inside the rope. This is also inside the rope. This is also inside the rope. Likewise. Okay, so consider a point here. Okay, there is a point here. So what will happen to this point? So this point, the force F is acting at this point, and you know that there is something called as intermolecular forces. So intermolecular forces is like if two molecules are there, there is an attractive force between both of them. Okay, so what will happen? This object A, molecule A and B are there. So B will attract A and A will attract B. Okay, it's kind of like a two magnets. Okay, if you imagine two magnets like this with the north and south pole, and again here south and north, what will happen? Both of them will attract. Sorry, attract. So what will happen? Both of them will attract to each other. So in similar way, you consider this point A and point B. What will happen? This B will attract A towards B, and A will cause a force on B. If we call this as force T, if we call this as tension T, this will also be T because of third law, right? So these are action, sorry, these are equal and opposite forces of attraction, equal and opposite force of attraction. So what will happen here? So because of this thing, there will be a reaction force here because of third law. This is action reaction pair, action reaction pair. So okay, we'll write it over again. This is T, this is T, and this will also be T. Okay, so what is this? This is action reaction pair. Similarly, what will happen? Because of this, this particle getting pulled like this, okay, this reaction is given by whom? This particle. So what will happen here? Again, this will be getting pulled. So that will also be equal and opposite. How it becomes equal and opposite, I will tell you again. Consider this A particle. Okay, consider this A particle. So at A particle, net force is equal to mass times acceleration, right? Mass times acceleration. So if I take m equal to 0, what will happen? Net force will be equal to 0, right? So net force equal to 0 means if I take this as T1 and T2, T1 minus T2 equal to 0. That means T1 equal to T2, right? That is how this will become equal forces. That's why I have written it as T1, T and T. Okay, so this is also T and this is also T. Similarly, this T and this T, they are this and this, they are equal and opposite pairs because they are intermolecular attractive forces. So whatever force it is providing on this thing, with the same amount of force, this B will attract A. So that's why they both are T. Again, when we are thinking about this force here, this is again action reaction pair. So what will happen? Again, this will be T. How? Using the same formula. So we are not considering the mass of the string. That's why m equal to 0, and whatever force is there, it will act along the same amount of tension will act at all the particles. All the particles, it will be T. Okay, so you can imagine this point now, B. Okay, point B, what is happening? Since it is, again, here also you can use net force equal to T minus F equal to 0. Why 0? Because M equal to 0. So M equal to 0 means net force equal to 0. That means T equal to F. So at this point, if you again consider, at this point, what is happening? This point, what is happening? It will be T here again because of force here. Okay, this is T. So here, this way also it will be T. And because of this pair, there will be a equal and opposite attractive force here, that T will be pushing this block finally. So this T and F is equal, right? In a massless string. In a string without mass, this T equal to F. That means this force is getting transmitted through the string to the object. You understand? So that means this string is acting like a medium to transfer this force. Okay. So that is the that is what is written here. String is acting like a medium for exerting force. Okay. So in a massless string, what will happen? The tension force will not vary along the string. In a string without mass, the tension force or tension along the string won't vary. Okay, that means it will be T equal to constant along the string. Fine. Now we will be discussing about string with mass. So this is a second case, right? So string with mass, we are saying that this whole string will be of length L. Okay, this is of length L, and it is being pushed by a force F, and this block is of mass M. And consider the mass of the rope as small m. Okay, small m. So now what will happen? Consider this point here. So here, because of this point being pulled by force F, it will have a reaction pair here, right? Action reaction pair. So that will be T. Okay. Now, because of this T, we don't know about the force here. So I will take it as T1. Okay. So at T1, so this T1 will cause what? An action reaction pair here. That will be T1 again, right? Or, 1 second. No, wait. So here, if you are taking these 2 points, A and B, so these are intermolecular attractive forces. So that will be equal and opposite. Okay. And because of this equal and opposite forces, there will be a force here which is trying to resist the pulling by T. Now, let's consider this point here. This point here. We want to check the force here, right? So, how we will be applying the second law? Net force equal to T1 minus T is equal to mass times acceleration. Okay. So mass here is not equal to 0. That means T1 is not equal to T. Right. So we got to know that the force is the action reaction pairs that is acting on this particle A is not equal. Now, with this T1 force, again, this particle here will be getting pulled because of intermolecular attractive forces. So, those will be equal. Again, there will be another force here. Let's call it T2. Why? Because again, at this point, if we take it as C, at this point, again, net force will not be 0. will not be equal to 0 since m is not equal to 0. So T2 is not equal to T1. Similarly, here it will be T2 and here it will be T3, which is not equal to T2. Here it will be T3 and here it will be T4 and this will be T4 again. So you can see that if string is having mass, then the tension will vary along the string. Okay, so tension is not constant here. Why? We will discuss about it more with a example problem. Then you will understand why it is not the same. Like why it is varying along the string. Okay. Now, now an example question here. So a string, like two blocks are connected using a string. This is a string, and okay, so this is a string here, and two blocks are connected with a string, and it is being pulled. One of the block is being pulled with a force F. So what will happen? Because of this string, this will also get pulled along with mass M1. Now, how to understand if it is a massless string or a string with mass? Because there is no mass given in the question, you can assume it as a string without mass. Now, we want to find the acceleration of the system and the tension in the string. So how to find the acceleration of the system? We will assume both of them, M1 and M2, as a single system, and which is being pulled by a force F. So net force equal to mass times acceleration. F equal to M1 plus M2 times A equal to F by M1 plus M2. Right. Now, we will assume a tension force here along the string. And as we have seen here in the previous theory, we know that in a string without mass, string acts like a medium for exerting force. That means the mass of, the tension along the string won't vary. If the string is considered as a string without mass, then the tension force won't vary. So whatever T we are taking here, you can take it here also. Okay. Now, to draw a free body diagram of M1, you can take M1 here. So M1, what is happening? F is acting towards the right side. T is acting towards the left side. And weight is acting downwards. And a reaction force is acting upwards. Here you know that there is no vertical movement, vertical direction. Net force equal to 0. That means N equal to M1G. And horizontal direction, what will happen? Horizontal direction. Net force equal to mass times acceleration. Net force here is F minus T, because if we assume the system is going to along F direction, that means F is larger than T. F is larger than T. So that is why we are taking F minus T, and that is equal to M1 times A. Okay. Now T equal to F minus M1 times A. What is A? F minus F by M1 plus M2 times M1. Okay. If you multiply M1 plus M2 and divide by m1 plus m2 to f, then it will be m1f by m1 plus m2. Then what will happen? This m1f and one m1f will cancel. So that will give you m2f by m1 plus m2. So you got the tension force in the string, right? So what is the tension force here? T equal to m2 f by m1 plus m2, and A equal to this. Okay. Now similarly, if you want to find the tension force using tension force using m2, you can draw the free body diagram here like this. So what will be the free body diagram of m2? That will be m2 here, and a T force is acting. So what is happening over here? Net force equal to mass times acceleration. So net force is T equals to, okay, here also reaction force and weight is there. Weight is acting downwards, m2g. So that is there. Since vertical direction, we know what is happening. N equal to m2g. So that is gone. Horizontal, what is happening? Net force is T, and mass is m2, and acceleration is A. So how to substitute this acceleration here? m2 times, A equal to F by m1 plus m2. So that's how we know that tension forces remaining constant along the string, right? Both the tension equations are, the expressions are equal. Now the next question. So here we have two forces. Two forces, and the mass is given. Mass of the block is given, not of the string. So again, find acceleration and the tension along the string. So with numbers, you will understand the concept better. That's why I have written it here. So what is happening over here? Because of this 15 Newton force acting along this towards the right direction on this 2 kg, what will happen? There will be a tension force acting to resist the pulling. Okay, resist the pulling. So that is T here. And since the same string is connecting to 3 kg mass, along the string of a string without mass, what will happen? The tension force will remain constant. So the same T will be acting on 3 kg mass also, and this is being pulled with a 10 Newton force to the left side. Okay, now we should see what will happen. Assume the system is moving along the 15 Newton force direction with an acceleration of A. We need to find the acceleration A of the system. So A equal to, okay, so first we will assume this whole thing to be one system, that is 2 plus 3, 5 kg. Okay, 5 kg mass is being pulled by 15 Newton towards the right and 10 Newton towards the left. So if you're taking this whole thing as one system, what is happening? So whatever force here, this T and this T, etc., are internal forces which are getting cancelled out. Okay, so you need to only think about 15 Newton and 10 Newton here. Okay, now, okay. So we can assume this weight of this object is 50 Newton, and there is this reaction force. And to find acceleration, you will consider the horizontal direction. So in horizontal direction, net force equal to mass times acceleration. Net force is 15 minus 10. Mass is 5, and acceleration is A. A equal to 1 meter per second square. Okay, you got the acceleration now. Now we know for this 2 kg block, this is object A, object B. So A block, we can draw a free body diagram here. So this is 2 kg. This is 15 Newton acting. This is T acting towards left. There is a reaction force and a weight of the object, 20 Newton. So vertical direction, if you consider, then N equal to 20 Newton. And horizontal direction, if you consider, net force is equal to mass times acceleration. Net force is 15 minus T is equal to 2 times A is 1 meter per second square. So that gives you T equal to 15 minus 2, which is equal to 13 Newton. Okay. Now, if you check the same with the 3 kg block, you can see that in 3 kg block here, T is acting towards right, 10 Newton is acting towards left, and N is there, and there is this 30 Newton. So the reaction force here is what? N equal to 30 Newton with the y-axis direction, if you consider. So if this is the axis, X and Y, so along vertical direction, y-axis, this is how it is. And horizontal direction, what will happen? Net force equal to mass times acceleration. Mass is 3 kg here. Net force is what? So here we are assuming that the whole system is moving along this 15 Newton force, that is towards the right side. That means T is larger. T minus 10 Newton is equal to 3 times A. See, if you take it the other way, you will be getting a negative sign in the T value. That means the sign is opposite, like the direction is opposite. That's it. So you don't need to think much about it. If it is opposing force, you should not take minus T and minus 10. That's it. If it is opposite force, take it with the opposite signs. Like for example, you can take T minus 10 equal to 3 times A, or 10 minus T also you can take as 3 times A. Whatever you're solving, when you're getting T with a negative sign, that means the direction you have assumed is wrong. Okay. So you don't need to worry about the directions over here. But intuitively, if you are thinking, you know that T must be larger. That's why it is moving along the right direction. Like this block B is moving along the direction of T. So T should be taken first, and then 10 should be subtracted from it. Now, this one, if you take, it will be like 10. Okay. So 3 times A. 3 times A plus 10 is equal to T. So 3 times A is what? A is 1 meter per second square. That means 3 plus 10 is equal to 13 Newton. So you got the same T over here and here. For block A free body diagram also, from there also you derived the same value. From the block free body diagram of block B also, you have derived the same value. So that proves our point that if you're not considering the mass of the string, it is going to be the same tension along the string at all points. Now, next question. So here you are seeing 3 blocks. Okay, 3 blocks. So block 4 kg and block 3 kg are connected using string 1. And block 3 kg and block 2 kg are connected with string 2. Okay. So if you consider this 2 strings, we have only talked about what? The tension along one string, T along one string will be constant, right? So if you consider 2 different strings, tension in both the strings will be different. Like if you consider this string to have tension T1, Then with this T1, the whole string will have the tension T1, and the masses, the force is getting transmitted to block 3 kg. So here also it will be T1. And in the string 2, this will be getting pulled with a tension T2. Okay. And this also, it is not necessary that it is always equal. That's the thing. It can be equal, but it is not always equal. Okay. So that's why we are taking it as two different tension forces. We will solve and see how it turns out to be. Okay. So we need to find what acceleration of the system and tension in both strings. That means A you have to find, T1 you have to find, and T2 you have to find. Okay. This is the question. Now, as usual, for finding acceleration, what do you have to do? You have to treat the whole thing as a single system, like 2 plus 3 plus 4, which is equal to 9 kg. 9 kg mass is one, you will treat it as one single system. So 9 kg mass is there, and there is this 18 Newton force pulling that, which exerts this when this 18 Newton force is exerted on 9 kg mass, an acceleration of this block moves with an acceleration of A. Okay, now this A is equal to, so net force is equal to mass times acceleration. Net force is 18 Newton, and mass times acceleration. Mass is 9 kg and acceleration is A. So A equal to 18 by 9, that is equal to 2 meter per second square. So you found the acceleration. Now, what do you have to do? To find T1, what you have to do is, okay, to find T1, you have to consider this as one system, this whole thing. So this T2 is an internal force in the system, so you don't need to treat T2 at all. So for finding T1, what do you have to do? Or from the first we will think about this free body diagram. So this is block A, block B, and block C. So think about this free body diagram of block A. Okay, so 4 kg is here, and it is being pulled with a force of 18 Newton, and T1 is acting along the 18 Newton, but in the opposite direction. And there is a reaction force N, and the weight of the object is 40 Newton. Right, 4 times 10 is the acceleration we are taking, 40 Newton. Now, vertical direction it will be what? N equal to 40 Newton. And horizontal direction it will be what? 18 minus T equals to 4 times A. How? Net force equal to mass times acceleration. So T1. So T1 equal to 18 minus 4 times A is 2 meter per second square. So that is equal to 10 Newton. Okay. Now we can see if the same applies with this B and C combined. So we will take B and C together. So B is 3 and C is 2. So that is 5 kg. It is being pulled by T1. So we will see net force equal to T1 equal to 5 times A. Okay. A is what? 2 meter per second. So that is 5 times 2 is equal to 10 Newton. So in any manner, if you derive, in the right manner, obviously, but in the correct, there are so many correct methods to find T1 or T2. Okay. So we will see about T2 also. If you talk about, this is B, this is B and C. Okay. This is B and C together. This is block A. Okay. This is A, B, and C. Now we will see from the diagram of B. Okay. From the diagram of B, what will happen? You take this block 3 kg block. So what is the free body diagram? There is T1 acting towards right, T2 acting towards left, and there is a reaction force N, and there is a weight 30 Newton. So N equal to 30 Newton here, and T1 minus T2, because we are assuming this particle to be moving along 80 Newton direction. So that's why I'm taking T1. I'm considering T1 to be greater than T2. So T1 minus T2 equal to mass times acceleration is 2 meter per second square. So we have already found T1. T1 is what? 10 Newton. And now we will see if T2 is equal to 10 Newton or not. Okay. If T1 equal to T2, what will happen? The net force will be 0, and the particle won't be moving. So that's why we have taken it as two different tensions. Okay. So 10 Newton minus T2 is equal to 6 Newton. So T2 equal to what? T2 equal to 10 minus 6 is equal to 4 Newton. We can derive this from C block also. So if you consider block C, so this is the free body diagram of block C. It is 2 kg being pulled by the tension force T2. So there is this reaction force here. There is this weight here. Okay. So T2 is doing what? T2 is pulling this block with the acceleration of 2 meter per second square. That is equal to 4 Newton. Okay. So what did you get? So acceleration equal to 2 meter per second square. And tension T1 equal to 10 Newton and T2 equal to 4 Newton. Okay. This is how you derive the forces. So the easiest way to derive, find the forces is by seeing the free body diagrams of A and C. Because here 18 Newton is given, T1 is given, acceleration we have already found. So equating, you will get T1. And to find T2, you know the mass of the object, acceleration is given, only external force is T2. So T2 equal to mass times acceleration, that is equal to 2 times. Acceleration is 2. So 2 times 2 is 4. So T2 easily we can find. T1, you have to equate the forces. That is just two opposite forces acting. One is 18 Newton and another is T1. Right. So now we will move on to something called as string with mass. So string with mass, we were saying about the case where you cannot neglect the mass of the string, like towing rope. Towing rope is you need that much strength. That's why most of it will be steel rope, and those kind of very rigid and very heavy ropes we will be using. So that's why you sometimes you cannot neglect the mass of the string. So this is string with mass problem. Okay. Another way to find is what the string mass of the string is given. So you should not neglect it. Then you have to use that mass to solve your problem. So a spring is lying on a smooth surface. So this is a smooth surface. Okay. And it is being pulled with a force F towards the towards the right direction. So it is being pulled to right direction using a force F. So this is the mass of the string. Now you want to find the tension at the midpoint of the string. So how to find the tension at the midpoint of the string? Suppose this is the midpoint of the string. Okay, sorry. This is the midpoint of the string. Okay. So you do one thing, just break this off, like not physically. You assume that you are breaking the string at the midpoint. Now you will get what? 2 pieces of this string. Okay. 2 pieces of the string. Okay. Now, imagine this mass m is distributed uniformly along the whole string. So the total, if you think of this rope as this particles, so uh, if one unit of length will have one particle, L unit of length will have how many particles? L particles, right? One unit length has one particle. So L unit length has L particle, right? Right. So here I am taking I so I'm considering that this whole string has L particles now. Okay, L particles now, and now if the mass m is distributed uniformly along L particles, that means all the L particles has equal mass. Okay, then what will be the mass of one particle? So L particle together has m mass. That means one particle will have one, sorry, m by L mass, right? One particle is what? One particle is one unit length. So one unit length will have m by L mass. So if this mass, this string is 2 meter in length, if if L equal to 2 meter and m equal to 3 kg, okay. So what will be one unit length mass? One unit length will have 3/2 kg mass. Okay. It is like this. Like suppose you think of a bowl of lemons. Okay, lemons. So small lemons are there. One bowl of lemons are there. Okay. So this lemon is one bowl of lemon. Okay. So this bowl has how many lemons? I'll say that it has 50 lemons. Okay. 50 lemons make 1 kg. Okay. No, that is too unrealistic. Maybe I'll take 5 kg. Okay. 50 lemon makes 5 kg. So what is the weight of one lemon? So 50 lemons has 5 kg. So one lemon has 5 by 50 kg. That's how it is, right? So that is equal to 1 by 10 kg. So the similar manner we are dealing here also. Okay. One unit length has m by L mass. Okay. So suppose this is L by 2. This is L by 2. And this is L by 2. Okay. So what is the mass of these two pieces? So this is equal lengths, right? Equal lengths are there. It doesn't seem like equal length. So I'll draw once again. Okay. So this is one string over here, and this is another string over here. So what will be the masses of these two strings? It will be m by L times L by 2, right? So one unit length has m by L mass, right? One unit length has m by L mass. That means L by 2 unit length has what? L by 2 unit length has m by L times L by 2 mass. Okay, that means m by 2 mass. That is very easy to understand because it is uniformly distributed mass, and it is cut at the midpoint. That means the equally distributed mass is now half. Okay, so that is why m by 2 mass makes sense. So this has m by 2 and this has m by 2. Now it looks like something of a similar kind that we have solved before, right? Like two blocks are there of given mass is there. How to find the action reaction forces if it is coming into contact? Like, I mean, if it is getting pushed or pulled, you will be taking this force here, and there is this T here, and this T will act on this one also. And that's it. Now, if you want to find T, what will you do? You will equate and find it, right? So this pulling will cause an acceleration here, A. And you need to find the acceleration and the tension of midpoint string. Okay. So now you know, to find acceleration, what will you do? You will take the entire, you will consider the entire string. That is like M mass is there for the string. F is the force, and net force equal to F equal to MA. So A equal to F by M. So that's done. Sorry, you were using capital M, right? So you will take capital M here so that the confusion is not there. Okay, F by M is mass times, F by M is the acceleration here. Now, you will take the free body diagram of A piece or A piece and B piece, like the two sections of the rope. So A section, if you're taking, for free body diagram of A section, this is A. Okay, this is M by 2. This is the force acting. This is the tension acting. This is the reaction force, and this is the weight of the section of the rope. So N equal to M by 2G. If you equate the vertical direction, and horizontally, what will happen? Net force equal to mass times acceleration. Mass times acceleration. Net force is F minus T. M by 2. Acceleration is F by M. So T equal to what? F minus M and M get cancels. Okay, F minus F by 2. That means F by 2. If you want to derive the same tension force from section B, you can find it like this. Section B is, this is M by 2. This is T. Now, acceleration is given. So net force is T equal to M by 2 times A. A is F by M. So F by M times M by 2, which will give you F by 2. So in both the ways, you are getting the same tension force. Okay, so that is how you deal with a spring with mass. Okay, I hope you understood the concept of how to find the mass of the section if you're taking. Now we will look on to more such questions to clear the concept. Okay, so that's all for this section. Thank you and have a great day.